So thank you for allowing me to speak today. Thank you, Stefan, for teaching me how to use big blue button. I think I was a very bad student. So what I'm going to speak about, and sorry, all my apologies for not being physically in the room, of course. So what I'm going to speak about are, in fact, based on two works, one by a joint work with Sylvain Lavau and Thomas Strobl, and another one to a joint work with Leonid Ryvkin. So first, I want to speak of something which is in some sense locally well known, but I cannot really find a place, maybe Reutenberg knows, I cannot really find a place where it's written down. It's fundamental of homotopy groups of Q-manifolds. And then I will explain how we used some results about singular foliation that relate singular foliations with Q-manifolds by Lavau, me, and myself, and Thomas Strobl, sorry, to apply these fundamental and homotopy groups to the problem of first return map, which is a very classical tool, first return map, but for a regular foliation. And basically, we have kind of defined, well, redefined, because there's some history behind, the first return map for a singular leaf of a foliation. So to start with, well, I presume I don't, well, the whole seminar was about, the whole Vienna was about higher structures. So Q-manifolds will be known from now. Just for me, what I call a Q-manifold, it's a special kind of differential graded algebra. So a graded algebra E with its differential Q. The only thing is that as a graded algebra, E has to be very special. It has to be, so E is called functions on the graded, it has to be functions on the graded manifolds, which means it is a section of the symmetric algebra of some vector, of some graded vector bundle. But here I will make this additional restriction that the vector bundles are considered, they are only in degree -1, -2, -3, -4, and blah, blah, blah. In fact, there will be even finitely many of them. Okay. So, classical examples of those, well, Lie algebroids, for A Lie algebroids, sections of wedge of A star with Chevalet-Eilenberg differential, that's a differential graded algebra, so it is a Q-manifold. And in particular, manifolds are Q-manifolds. Now, these were just to define objects. Yeah, and also with my conventions, functions are of a positive degree, and functions of degree exactly equal to 0 are the same thing as ordinary smooth functions on the base of a manifold. Also, morphisms. Well, morphisms between Q-manifolds is just the same thing as a morphism from a Q-manifold E to a Q-manifold E prime. To me, is going to be, in fact, a graded algebra morphism, a differential graded algebra morphism from E prime to E. So it's defined by a pullback, so you have to reverse order. Is there any question on that? So this means in particular, so since a morphism from EQ to E prime Q prime With this convention, it's in some differential graded algebra map from E prime to E, differential graded algebra morphism. Well, in fact, it has to be given by some map phi from M to M prime, then all kind of maps, vector bundle morphisms from Sk of E to E prime, which phi k maybe, which are vector bundle morphisms over the first vector bundle morphism I just defined here. Just to make a concrete what this abstract definition is. Okay. Now, I'm going to tell something which might be not exactly true if you work with infinitely many vector bundles over a manifold, but I want to skip this kind of details. Well, products of Q-manifolds are Q-manifolds. Yes. So this is a perfect way to define a homotopy. Well, what is a homotopy between two morphisms of Q-manifolds from E to E prime? Well, it's a Q-manifold morphism like this from E times 0, 1 to E prime, whose restriction to E times 0 or E times 1 are just phi and psi. Right? And well, it's just what you expect. I mean, it's just Q-manifolds are like manifolds, which things I'm going to repeat quite a few times. An interesting point is that since you can define like this, a very simple way, homotopy classes of morphisms between Q-manifolds, you immediately have defined what homotopy equivalences between Q-manifolds are. Two Q-manifolds are said to be homotopy equivalent.
Camille,
when you have a pair, yes?
Don't you want to put like the tangent shifted by one of this interval for the homotopy? Or?
Yes. Yes. Okay. What do I mean by 0, 1 here? It's not very, okay. By this thing, 0, 1, I mean 0, 1 seen as a Q-manifold, which means its forms on 0, 1 equipped with the RAM differential. Or maybe it would be more correct to say, as you say, it's T1 of 0, 1. Like this. So anyway, as a differential graded commutative algebra, it's this. Yes? Do you agree with this? Well, I know that if you want to, if you have infinitely many vector bundles, E minus 1, E minus 2, E minus 3 goes to minus infinity, this might be argued. That's not the correct definition. This is what we did in our article, in fact.
Yes, sorry, I didn't have the phone, the micro. Yeah, I agree.
Okay. Again, infinite case is a bit annoying for convergence reason. Yeah, so if you, whatever the category is, if you have defined homotopy equivalence of maps, you have implicitly defined, you have implicitly defined a homotopy equivalence of Q-manifolds. Just say that two Q-manifolds are homotopy equivalent when you have a map like this, so that the composition is homotopic to the identity here, and the composition like this is homotopic to the identity here. Okay, so now we have defined Q-manifolds, we have defined their morphisms, we have defined homotopy of their morphisms, and we have defined homotopy equivalences. Those guys. So I want to define the fundamental groups. And how to define the fundamental groups of whatever. It's maps from S1 or Sn to the whatever, but which have to be a constant near some point, near the North Pole. So for this, I have to define something very stupid, is that when I have two Q-manifolds, and the first one is a manifold, in fact. The first one, just this, omega m with the RAM differential. And the second one, oh, I shouldn't call it m. I shouldn't erase everything either. Okay, so I have a map from a sigma. So as Thomas said, maybe I should call it T1 of sigma to some Q-manifold EQ, which is with E being over some manifold M, and I pick up a point M in M. What does it mean to have a constant map of Q-manifolds between sigma and M? It's not, well, it's not totally obvious. What I want, in fact, is to have a Q-manifold morphism, which is as stupid as can be. I mean, the whole manifold sigma is mapped to M, and the whole tangent space of sigma is just mapped to a 0. Or if you want to see it as an abstract differential graded commutative algebra, where all my algebras are commutative by convention in this lecture, I just define it like this. So I take a function f here, I just trash whatever is of positive degree, just keep the functions in the base a manifold, and I evaluate it at m, and I see it as a constant function over a sigma. Okay, all these are just words to say that perfectly fine to define a constant map from a manifold to a Q of a manifold. That's all you need to know. And from them, it's in fact extremely easy to define the pi n and also the fundamental groupoid of a Q of a manifold. What is pi n based at a point m? So m is the base manifold of the Q manifold EQ. Well, it's just homotopy classes from a sphere to EQ, which near the north pole of the sphere, the north pole here, in a neighborhood of it, has to be a constant map equal to m. And the fundamental groupoid, well, it's the same idea. Just take some interval, you map it to EQ, EQ is over m, and what you want is that in neighborhoods of this point and neighborhoods of this point, well, you have in fact constant map equal to a point here and equal to a point here. I mean, definitions do make perfect sense. Well, when you speak of homotopy classes, you have to take a homotopy which are themselves a constant near the boundaries. But again, I'm going to repeat it many, many times. Just things are Q-manifolds are like Q-manifolds. Okay? Are like manifolds, I mean. Is there any question on this? Okay. So then continue. Well, and okay, that's of course a slightly vague statement, but if it's blank, it's because I'm going to make it more precise now. But all usual properties of fundamental groups or homotopy groups or fundamental groupoids are true. So, for instance, let me write some of them. So pi n, sorry, of E valued at some given point m is a group. That's exactly. You don't even have to reprove it. I mean, it's kind of given for free. It's of course abelian for n greater than 2. And the fundamental groupoid, well, is a groupoid. Right. Well, I'm pretty sure, although we, yes?
What is M here in the groupoid?
Oh, sorry.
Yeah,
no.
Should be no M.
The groupoid over M. But I'm pretty sure that all these usual properties about if you have the fundamental groupoid on U and on V, then you have an exact sequence with the pi one of the intersection, the pi one of the union. I mean, I'm pretty sure that all these kind of things are going to work exactly in the same way. I'm even not going to write them down here. But this, I'm pretty sure it works exactly the same. And an interesting point is that, again, by construction, I mean, the fundamental groupoids and the homotopy groups, they are the same for any Q-manifold, which are homotopy equivalent. It should be more precise and to say that a homotopy equivalence between two Q-manifolds induce group isomorphism of their fundamental group or of their homotopy groups. But, I mean, it works exactly again as one expects. Yeah. So, and basically, the proof of this is just by construction. There is really nothing to prove. So, in fact, what is interesting, well, again, there is some category of theory hidden here. So I'm not going to give, I don't want to enter it, is that not only it's, we have defined, well, redefined, because somehow, as I said, it's locally well known. Homotopy groups, fundamental groups and fundamental groupoids of an arbitrary Q-manifold, but in fact of an arbitrary class of Q-manifolds up to homotopy equivalence. Okay, so let me give examples. And so none of these examples are really, by the way. Well, for a manifolds M, what are the pi n? And what are the fundamental groupoids defined when you see the Q manifolds as, when you see the manifold M as a Q manifold? The answer is as easy as you think. Well, it's just the usual homotopy groups and the usual fundamental groupoid of the manifold, nothing more. For Lie algebroids, it's quite interesting. So that's an example which is due to Braik and Zhu. So for Lie algebroids, what is, for instance, a Lie algebroid? I can see it as a Q manifold, it's just A of 1, M with Chevalier-Eilenberg differential. So what is, in this case, the fundamental, for instance, the fundamental groupoid? A of 1. Well, in fact, it is the Weinstein groupoids, or whatever name you call it. It is a groupoid that integrates A. So it's exactly the groupoid which is made of homotopy classes. Some people call it also the Reutenberg groupoid of homotopy classes of A paths in the Lie algebroid up to a homotopy. So, yes?
Did you want to say Severa groupoid?
Yes, what did I say?
Reutenberg.
Oh, because I just saw his name in the...
No.
Right, yes, the Severa groupoid.
Yeah.
I think it was probably first written by Severa. Thank you, Thomas, of course. I mean the Severa groupoid. Yeah, what was I saying? Yes. Okay, so in fact, it is the simply connected groupoid, which may not be Lie, by the way, which integrates the Lie algebroid. Now, what are the pi n? well, just take this Lie groupoid, the pi n at a point m of A of 1 at m. In fact, so this is the example by Ryvkin. In fact, it is the pi n in the usual sense of the m of a fiber of the groupoid gamma. So this is S minus 1 of m, with S from gamma to m being the source map. Okay, so it's kind of funny. The fundamental groupoid is in fact the groupoid, the Lie groupoid, which may not be Lie, that integrates it. And the pi n are in fact the pi n of the S of the fibers. Okay. Another example, well, Lie-nifty algebras are also Q-manifolds, right? They are just Q-manifolds for when M is a point. So it's a result by Berlund, someone who works in derived geometry. And well, so what is it? So by Lie-nifty algebra thing by E-2, I mean a Lie-nifty algebra which is built on graded vector of a bundle which is of the form E-2 plus E-3 plus E-4 plus blah blah blah. Right? And I should not have written it this way. Well, after some computation, you see that, well, on an Lie-nifty algebra, of course, you have a differential D that I should write here. Yeah, and the pi n is going to be exactly the cohomology in degree minus n of this complex. So, yeah, well, and in general, so after I've kind of claimed that it was highly interesting, I'm going to say something extremely disappointing. Oops, sorry. Well, just a remark. So when you have a Q-manifold, you have leaves on the base of a manifold. And by n of some Q-manifold, EQ, based at the point M, in fact, it only depends, that's only to see, on the restriction of that Q-manifold on the leaf of M. Right? Basically, you cannot jump from one leaf to another leaf. So in fact, it's defined on each leaf. And on each leaf, you have a groupoid. And so in some sense, the Q-manifold on that leaf, it's some transitively algebroid plus, well, a nilpotent Lie-nifty algebra. And with a Leonid, we basically, I'm not going to give the detail, but we found some exact sequences that allow to compute this guy out of, well, the pi n of the fiber of the groupoid gamma, groupoid that integrates the transitively algebraic that you have on the leaf of M, and, well, what you obtain by taking...
Sorry, why Lie algebroid now?
Okay, I'll be more precise. If you have a Q of a manifold, do you agree that you have an induced a singular of a foliation on the base of a manifold? Yeah? Now, take a leaf of that singular of a foliation. The Q-manifold restricts to that leaves. Yeah. So on that leaf, the anchor map, I call L this leaf, is just onto by definition of the leaf. Since it is onto, well, also you can check that the map D from E-2 to E-1 has constant rank on that leaf. Okay? Since it has constant rank, E-1
can take the quotient
divided to D-2 is a honest vector bundle, and in fact is a Lie algebroid, a transitive one. Yeah. So it has a groupoid. Oh, I need to plug my computer, sorry.
Is this one always Lie? It's a Lie groupoid, right?
It is, yes.
Yeah. Mm-hmm.
So I have to move a little bit.
Maybe Leonid can continue.
Camille, do you hear me? Because we don't see you and we don't hear you. Camille? Ah, we see you again. We don't hear you though. He cannot hear me? Like Alexei? Camille, use the speaker.
Leonid didn't react either. Maybe he's not listening.
Do you hear?
Yes.
Okay,
now,
so
yes.
There was a short electrical cut that put the Wi-Fi down.
Ah,
but it's back.
Yeah, we will add this. We will add 5 minutes for this, okay?
Okay, sorry. So I'm back. Do you hear me well now? Yeah. Good. Okay. Sorry. Another work in progress in my building. Maybe it's that. So, yeah, basically finished this. So I just wanted to say that one of the results with Leonid gives a kind of recipe to compute this pi n, with this kind of disappointing thing that it only depends on leaves. So about leaves, perfect transition, I'm going to speak about singular foliations. So to say it in one word, well, regular foliations, it's like foliations where all leaves have the same dimension, while on singular foliation, you allow to have some leaves that may be of different dimension. Well, there has been a historical debate, which is now over to me. But do you see what I write? Yes?
Yes.
Yeah. Which is now over, which is what is a good definition of a singular foliation. So let us say that there were some convergence to this definition. You define singular foliation through vector field tangent to the leaves, and it is now, by definition, a subsheaf of the sheaf of vector fields, stable under multiplication, stable under Lie bracket, locally finitely generated over infinity of M. Notice that this condition, which is very important, in fact, otherwise you have very annoying examples. If you decide to work in the algebraic or holomorphic case, it's automatically true because of Noetherianity. Okay, so that's our definition now of singular foliation. Example, well, when you have a Q-manifolds, as I have defined it, EQ, well, you take E minus 1, you have, when you take the dual picture, the anchor map that goes from E minus 1 to Tm, and you take F to be rho of all sections of E minus 1, and the condition Q square equal to 0 implies that F is a singular foliation as defined above. Okay. Okay, so well, you have arbitrary definition. I just want to mention. So some people, as you see, this talk was initially given in French. So as you see, you can also define with compactly supported vector fields. This makes no difference. I mean, all these definitions are equivalent. Okay. Yeah, I just wanted to say, well, I'm going to skip this. Well, examples. If you have a Lie algebroids, the image of the anchor map is a singular foliation. So Lie group actions, symplectic leaves of Poisson manifolds, regular foliations are examples of singular foliation. And there is still this extremely annoying open question by Androidakis and Zambon that says that any singular for any singular that asks if it's true or not, that any singular foliation is the image of a Lie algebroid through the anchor map. In the neighborhood of a point, it's still open. Okay, I think I will, well, just to say that there are quite a few examples of singular foliation which are not at all of Lie algebroid type. For instance, vector fields on R2 that vanish quadratically, that can do whatever on R2, but have to vanish quadratically at a given point. That's absolutely not sure whether it comes from a Lie algebroid or not. But you can also take polynomial vector fields that kill some given polynomial function. Easily seen to be a singular foliation in the sense I gave, but there is no Lie algebroid in general. However, okay, I'm going to reorganize a little bit in a different way because, oops, okay. However, I just reorganize my lecture. I'll come back to this after. Even if there is maybe no Lie algebroid behind a singular foliation, you can show that there is always a Q-manifold behind. So Q-manifold being Lie-infinity algebroid, it's kind of generalization. So first I give the statement under a vague form. It's behind almost singular foliation. There is a natural Q-manifold, what we call the universal Q-manifold. And why universal? Because it is in fact universal in the category of Q-manifolds that define not maybe F, but a sub-foliation of F. So it's really a universal object in the category of Q-manifolds. The more precise statement goes like this. Okay, if you have a singular foliation, you have to say that generators are not too bad. But I mean, in most of the cases, that's true. Yeah. In most cases, that's true. And if you are on a relatively compact open as a subset, then you can do this. F as a infinity module, it admits a resolution of finite length by sections of vector bundles. Well, you can check that this vector bundle admits a Q-manifold structure, and any two such Q-manifolds are homotopy equivalent. It's a kind of homotopy transfer theorem, but it's not exactly homotopy transfer theorem. You replace F, your singular foliation, which can be nasty as a infinity module, to a projective resolution, which by Serre-1 is the same thing as some vector bundles. And you construct a Q-manifold structure on that vector bundle. So what we showed with Sylvain and Thomas, is that this construction more or less always work. And it makes very first sense when you have a singular foliation to call homotopy classes of these Q-manifolds the universal Q-manifold of a singular foliation. And since it makes sense to speak about it, it also makes sense to give it a name, UF. So UF stands for the universal Q-manifold, which is behind F. Okay, so now, what is the homotopy group of a singular foliation? Now it makes sense to define it as being the homotopy group of its universal Q-manifold, since we have defined, since to a singular foliation, we have associated the homotopy classes of Q-manifolds, and two homotopy classes of Q-manifolds, we know how to construct the pi1 pi n. Okay, so just to explain where it comes from, well, if you know Androidakis Scandalis holonomic groupoid, it's highly related. So it's related to this, but of course, if you don't know this groupoid, this may not be very relevant. So pi n of f involves the pi n of the leaves, the pi n of the isotropy groups of the leaves, because you have a Lie group associated to any leaf, which is 0 if and only if the leaf is a regular one. And it involves star of Fr. So it involves like the cohomology of F seen as a safety of a module over R, where R is just the evaluation at a point. So, I mean, it involves quite a few natural things. Okay. And just keep that. So now, I'm just going to finish with that. I have 1 minute. I'm just going to give the main result. I want to give it this one, and I stop after these slides.
Yeah, 2 minutes, I guess, right? Yeah.
Okay, two minutes. All right, so let me first do, let me draw something. Well, when you have a regular foliation, you have a leaf, and you have the first return map. First return map is, well, you start near that leaf, you follow this path, and when you come back, you are at a given point. So when you do all that, you get a map from the pi1 of the leaf L to diffeomorphisms of the transversal T. For singular foliation, the story may be a bit different. Think of the example of the self-eating snake, where you have a leaf which is a circle like this, and the other leaves are like a snake that are going to eat themselves. So it's like a cylinder, but which gets smaller and smaller and gets into itself. The problem is that you have this circular leaf, which is special here, but you have no natural way to define the first return map from here to here, because you don't know at which point you want to arrive here. So what we said, basically, is this. So first, when you have a leaf, you have a notion of a transverse singular foliation. Think Weinstein splitting theorem for Poisson manifolds. It is the same thing. And what we were able to construct is a sequence of maps with Leonid that go from just the ordinary pi n of the leaf to, well, forget these sections for a moment, to the pi n minus 1 of the transversal foliation. So defined as it was before. And moreover, we show that there is a long exact sequence with pi n of the leaf, pi n of the big foliation, and pi n of the transverse foliation like this, with our holonomy maps being here. And we suggest to call these holonomy maps the higher first return map for a singular leaf of a singular foliation. Just to say that in fact, it's just a generalization of some work long time ago by Olivier Brahic and Chen-Cheng Zhu that have the same long exact sequence for Lie algebroid fibrations. In fact, our work can be just seen as a generalization of it. Basically, it's to extend from Lie algebroid fibration to Leaf-T algebroid fibration. Also, we also recover some old results by the Dazor. But just last sentence to make the conclusion. What is interesting here is that when you think of the question, what is the first return map for a singular leaf of a singular foliation? A priori, there is nothing like Q-manifolds on it. I mean, it has nothing to do with Q-manifolds. But since, in fact, singular foliation, due to this result by Lavau, Strobl, and me, are somehow the same thing as Q-manifolds of a certain type. In fact, the natural answer involves Q-manifolds, although it doesn't seem to be the case at first look. Thank you very much for your attention, and sorry for this internet problem.
Okay, thank you very much for your talk. Other questions? Here in the lecture hall?
Okay, maybe I come back to my seat.
Or are there online questions?
Yes.
Please go ahead, Dima.
Hi, it's Dima.
Oh, yeah. Sorry for the confusion of name, Dima.
It's okay. It surprised me a bit, but all right. But yes. So you raised a couple of questions there, and so I just wanted to remark that there's so that to every such NQ manifold, you can associate a simplicial pre-sheaf on the side of manifolds or in super manifolds, and so that's basically, that represents a stack, and there is a standard way to to construct homotopy groups of such stacks. So and these are actually sheaves of groups. Not just discrete groups, and that's so what's involved here as well, whereas you have like an actual single point, which is why you're constrained to stay over the leaf, but you need to parameterize over arbitrary basis, so that you actually get a sheaf of groups, and then you can grow across leaves. So I'm going to I'll send you a link in the chat where this is pointed out. But this is well, the construction of these homotopy sheaves. That's this is standard for for any such infinity stacks. It's from Lurie's book. And yeah, I think that's when you parameter base is just a point. I think that's what you recover what what you wrote. So if you want to
agree. That's why I said it's kind of locally well known. By the way, I didn't use this Lurie reference specially, but as a Severa really means Severa this time. Explain me quite a few things about those. I totally agree, but I spoke everywhere with pi n of EQ based at a point m. But in some sense, it's not the most relevant thing. In some sense, what we really use are sections. This, like, in fact, it's our maps from from m times, so T1 of m times Sn to EQ.
Right,
that's in fact what we're using everywhere.
That's precisely
really at a given point.
Talking about, yes.
And that's much more relevant because, as I say, pi n itself is just related to the leaf. On a leaf, you just have a manifold on an LNFT algebra, kind of twisted. Not so interesting. But sections, it really goes in the transverse direction because smoothness gives some constraints.
Mm-hmm. Precisely.
I totally agree. But yeah, with the paper with Leonid Ryvkin, in fact, what we use is not really the pi n. What we use is this.
Right.
But please, if you have a reference to give me, that's good.
Yeah, I look forward to reading that. Thank you.
It is online.
Yeah.
Okay, are there further questions?
Hi, I remember that in some other talk you once said that what you found with Leonid was some generalization of this obstruction of Kreining and Fernandez for the integration of Lie algebroids to Lie groupoids. Can you explain like where in your sequence you have this obstruction and how this works?
Yes. So this map here, take n equals 2. It goes from pi 2 of the leaf to, well, pi 1, but in fact it's sections of pi 1. So to pi 1 of this guy. So if I take m equals L to simplify, it goes to pi 1 of the transversely algebroid. So transversely algebroid, pi 1 the transversely algebroid, in fact, is just the isotropy groups of, it is a group that integrates the isotropy Lie algebra. So I should say, can I just erase this? If you spell it out entirely, with m equals L, you go from pi 2 of Lm to the group that integrates the anchor of rho at L. It is a group. How do I call it? Like a group that integrates this. The simply connected group behind that. So what is it? But in fact, right? It was already in Ryvkin.
That's a Lie group, right?
But what Kreinig does is in fact this, right? But from here to here, you have the exponential map. And what we find is the composition of Kreinig-Fernandez map with the exponential map.
So you say that this pi 1 of the transverse foliation is, in the end of the day, this Lie group G tilde?
Yes. Yeah, because a pi 1 of a Lie algebra, when you see this Lie algebra as a Q-manifold, in fact, it's simply connected Lie group.
Sure. Yeah, sure.
So that's why this guy appears.
And why
but in fact,
and why is the first map the Kreinig-Fernandez map?
Well, this you have to look at the construction. It's not totally obvious, but it's kind of natural. I mean, so you have like, in fact, by the way, it is evaluated in the center. Okay, everywhere, also here. Why is it?
So wait. So well, where's the center?
So, in fact, so. Yeah, when m equals to L here, it's always true that the map from pi 2 of L to pi 1 of the transverse thing, in fact, is valued in the center of this group. I mean,
this Lie group, okay.
It's not. That's kind of well known. If you just think of foliations of manifolds, right? But you have such a long exact sequence also. You know that the pi 2 of n is mapped to the center of pi 1 of k. You have exactly the same phenomena for the long exact sequence between manifolds of foliations. It's not surprising to get to the center here. Again, it's just Q-manifolds are like manifolds idea. Yeah, so why is it in the center? Well, because okay, what you have is a map from a sphere to the tangent space of a sphere to A, right? And the idea of this map is, well, you take a small, first you take like paths like this that go along the sphere and that at the end finish here, right? And when you do that, you see that by construction, yeah, it's not totally trivial. But in fact, better answer, you just have exactly the same phenomena when you just work on manifold foliations. It's because when you have a sphere and you lift it, you obtain a kind of sphere that opens like this. And you can see that when you do this, then this open sphere, then the same path backward, you obtain something which is homotopic to this. You have a natural homotopy.
Okay,
of, I mean,
roughly.
This path here, if this sphere exists, this path here is homotopic to this. Take it maybe in another color. Like this, in green is homotopic to these, too many colors. Okay, assuming that this path is a boundary of something, I'm claiming that the black path is homotopic to the green path, like this, then like this. That's basically the idea.
Okay, thank you.
And it's not related to Q-manifolds, it means homotopy theory.